No questions? Okay. It's on, right? Okay. So where we were last time, so we kind of had like a sort of overview derivation of ADS CFT from the original stringy story that of the near horizon limit and all that in D3 brains. So, and then what we did was we basically started looking at ADS CFT correspondence as a more general idea where the presence of an asymptotically anti-de Sitter space in gravity in asymptotically anti-de Sitter space, the quantization of that we believe is a CFT. Okay, on very general grounds. So in some sense you could almost think of it as a definition of what quantum gravity in asymptotically anti-de Sitter space is. If you give me a CFT in some dimension, asymptotically ADS d+1 quantum gravity is defined by that CFT. So the question in some sense becomes, in what regimes does this CFT capture Einstein gravity and its quantum corrections? So that's a semi-classical gravity, when does it manifest itself, and what would be the definition of, let's say, string theory in asymptotically ADS space, etc. So those questions, the full definition of string theory in asymptotically anti-de Sitter spaces is not known. In fact, the full definition of string theory in asymptotically flat space itself is not known. Okay, what we know is we know perturbative string theory. We know how to do it in flat space in general. In 10 dimensions, string theory tells you what the dimensionality should be and what the compact dimensions, etc. are. So various degrees we have control on that. But even perturbative quantization of string theory is a little bit tricky, and opinion is somewhat split about whether it has been successfully accomplished or not. Okay, so there are people who claim, using certain strategies called pure spinor technology and all that, to say that it has been quantized in ADS. But generally speaking, because if you remember, one of the fields that we had in our theory was what called an RR form field, right? And in string theory backgrounds where RR form fields are turned on, are generally speaking not amenable to easy quantization. Okay, so perturbative string theory itself is a little tricky to define there, and non-perturbative string theory anyway, even in flat space we don't know what it is. So in ADS, what you can think of the n equal to 4 super-Yang-Mills theory is as a non-perturbative definition of string theory for this asymptotically ADS theory. Okay, so this is sort of the way to look at it. So what we did was we kind of took that as our jumping off point, started with ADS ADS geometry. So ADS geometry is basically the vacuum of the theory, and we want to look at that and look at fluctuations around it and think of that as the CFT ground state and fluctuations around it. That's the way we are going to look at it. So yesterday what we did was we wrote down the ADS metric, and if you have not looked at that part of the lecture, you should definitely look at it, because that will affect a lot of the things that I'm going to say, and it's a very simple and basic ingredient. And there's a geometry of ADS. If you know, a lot of the things that you actually talk about CFTs will also become clearer in some sense. Okay. So what we concluded with was the fact that the isometries, like just as flat space or Minkowski space has Poincare symmetry as its isometry, for empty ADS space has SO d,2 in ADS d+1 had SO d,2 as its isometry. Okay, it's the isometry group. So the point was that the isometries of the vacuum you think of as the symmetry of the theory itself. Okay, so quantum gravity in ADS, quantum gravity built on the ADS d+1 vacuum, you think of it as having the same symmetry group. So unless there is symmetry breaking, symmetries are realized in the vacuum. So that's the general idea. So the natural thing, if you believe in holography, is that you should look for a d-dimensional theory in which has this symmetry. And the point is that, if you remember, one of the metric, one particular form of the metric that we wrote down for ADS space was of this form. So this is d-dimensional, and this together gives you ADS d+1. Okay, so this is called the Poincare patch of ADS, and here it's clear that there is, if you r equal to constant is your holographic screen, there is a Minkowski space sitting here. Okay, so it's very natural to look for a theory which is living in conventional, our Minkowski space, but at the same time has a symmetry group which is SO d,2. Okay, so this would be, so the idea is that so SOD comma 2 is actually sufficiently big that it contains the Poincaré group of Minkowski D. Okay, this Poincaré group of this can be contained inside this. Okay, and that's what such symmetry groups are basically. Such theories are well known. So there exist quantum field theories which have this enhanced symmetry. Okay, not just the, so this would be SOD minus 1 comma 1 times translations. Okay, so this is what you would typically think of as the symmetry of a standard Poincaré invariant quantum field theory in Minkowski D. Right, that's your standard expectation. But the claim is that there exists, you want to look for a theory which has this property, but the interesting thing is that such theories have already been studied for various reasons, and that those are basically what conformal field theories are. Okay, so if we had, so CFTs have SOD comma 2, CFTs in D dimensions, have SOD comma 2 symmetry. See, now I'm talking about them as a symmetry and not as an isometry, because isometry is a symmetry of a specific geometry. Okay, what we are really saying is that we are looking at the ADS D plus 1 spacetime, which is a given metric, which you should really think of it as a state, and that state, it has this in the bulk language or in the metric language, it has an isometry realized in it. Isometry basically means that if you do a coordinate transformation, the metric form doesn't change. Okay, so generally speaking, if you do a coordinate transformation, the matrix form will change, but diffeomorphisms are, our understanding of diffeomorphisms is that the metric is still thought of as the same. Okay, geometrically they are the same object, but its form will change. So that's what a diffeomorphism generally speaking does. But there exists a class of diffeomorphisms which basically do not even change the form of the metric, and those are what are called isometries, and most spacetimes typically do not have any isometries. Okay, so that's what, Minkowski space is an isometry in Cartesian coordinates, only in Cartesian coordinates, which is basically Poincaré symmetry. Okay, similarly here, this geometry, the isometry is the property of the metric again. Okay, that's also an important thing to emphasize. So Minkowski space has Poincaré symmetry as an isometry, but it's manifestly realized in Cartesian coordinates. That's the more precise way to say it. So here on the other hand, we might not be able to realize it manifestly, unless you do it in embedding space or something like that, the full symmetries. So this, for instance, you can't see all of the isometries by looking at this spacetime, looking at this form of the metric. But you can check using your Killing equations and all that it is there. Okay, or you can use some other embedding space and some things to actually sort of make it clearer. But anyway, so the point that we are taking away from it is that it has a symmetry, and that symmetry is basically the symmetry that we see in the conformal field theory. Okay, so what is the point? So Poincaré, so we know that, let's count the generators of this symmetry. Okay, so we know that this, if SOD comma 2, except for some signature change, etc., is basically the counting of generators will work the same as SOD plus 2. And in SON, we know that the number of generators is basically going to be this. Right, it's a symmetric matrix. So that means the generators will be symmetric matrices. So this will be the number of generators of this SOD comma 2. Okay, and we know how many generators are there here. So here there are the Lorentz generators coming from the Lorentz group. Okay, how many are there? No, that's in 4 dimensions. Here we are writing it in general D dimensions. Yeah, so we have D into D minus 1 by 2 generators here, and then we have D generators here. Okay, so if you subtract this from this, you should basically find D plus 1 extra generators inside SOD comma 2. Okay, so these extra D generators are called the generators of special conformal transformations. So I'm going to write down a few things which are just, you can go look it up if you want. So we can't cover everything in great detail, but I think what I'm saying is sufficiently, it'll be enough of motivation to kind of not make it look too magical. Okay, so so this is what is called the D part is called the special conformal transformations, and the extra one guy is what is called a dilatation or a dilatation. Okay, so these are the two extra, so this is just a name for the extra generators that are there inside SOD, 2, which are on top of what we typically have in Minkowski space. Okay, Minkowski space quantum field theories always have this much symmetry, but there exists a special large class of theories which have this extra symmetry, and those are called conformal field theories. Okay, so let me call, so the generators of these guys are typically sometimes called L mu nu, the generators of Lorentz transformations, and these guys are translations P mu, so this is the full Lorentz guy, and this is usually denoted by D, and this is denoted by K mu. Note that it is a vector because it is in D dimensions. Okay, so it's in some sense very similar to P mu. So kind of like you can very roughly think of, so if you think of, so you can think of P mu as kind of like an antipodal, so if you think of space-time, so conformal transformations are, you can think of Euclidean, at least in Euclidean signature. So this is, many of these things that I'm saying about, so I'm talking explicitly in Lorentzian signature because we are fundamentally always interested in black holes. And black hole information paradox is a very Lorentzian problem because it's a time-dependent problem. If you just want to count entropy, etc., it's not so much Lorentzian. But if you're interested in like time evolution and Hawking radiation and things coming back and unitarity, this thing, etc., unitarity is a very Lorentzian idea in some sense. Okay, so we are definitely interested in Lorentzian signature. So all my discussions here are in Lorentzian signature. But many of the discussions that you might see in various books for conformal field theories, and many of the many people who are interested in, let's say, more condensed matter like applications, right? For instance, if you are interested in Ising model or critical exponents and things like that. So then you will more often be interested in the Euclidean version of these discussions, and there are some parallels there. Okay, so but it's somewhat easier, at least to motivate special conformal transformations. It is easier to kind of think of it in terms of like a Euclidean plane. Let's say you can, most of these things you can think of just in 2 dimensions. So the Euclidean plane, if you do a conformal transformation, you can actually map it to a sphere. So this is basically the projection that all the books that you've seen. So this is the the Riemann sphere, if you like. Okay, so what you're essentially doing is that you're adding a point at infinity to compactify the plane. Okay, so that's really what that is, and that construction. So one way to kind of think of special conformal transformations is you can, it's a bit like, so what special conformal transformations are to, so what translations are to the origin of Euclidean space is what special conformal transformations are to the point at infinity. That's roughly the way to think about it. So there is a sense in which you can do an inversion. Well, I don't want to get too distracted into it, but so if you do an inversion, a translation and another inversion, you will basically end up generating essentially a special conformal transformation. Inversion means x going to minus x going to x mu by x square, if you like, or minus x cube by x square, slightly more precise. Okay, so I'm just giving you some general way to think about it. It's not be thought of as it's an analogy, and the only thing I want to emphasize here at the moment is basically that this is, again, it has 4 components. Okay, so this is, you should not think of it as it's not translations. They're not translations, but there is a sense in which it is something like a translation, but a translation in which it moves sort of the point at infinity in some sense. Okay, the point, if you do ordinary translations, the point at infinity remains fixed. See what I'm saying? So that's roughly the way to kind of get some intuition for this. So anyway, so the point is that we have these D+1 generators that you have, which is what the symmetries of this guy. This is just purely a discussion about the symmetries, SOD, 2. Okay, but then if you want to say that this symmetry is actually a symmetry of some theory, so the way in which you typically think about, you first want to say that so there are theories in Minkowski space which are invariant under these transformations. under these transformations. And so this is what we mean by a transformation. Okay, so these generators, so an alternate way to define SOD, 2 is as so the Minkowski metric basically goes to an overall conformal factor times the same Minkowski metric. So note that this is typically when you do this transformation, so if you did not have this piece here, this would basically define Poincare transformations, right? Because they will just basically give you isometries of ds square. Note that it's very, for at least for the moment, it's very important that this ds square stands for the standard Minkowski space. It's not a general statement about an arbitrary curved space or something like that, at least not at the moment. So it is basically just a statement about Minkowski space and how it transforms. Okay, so you get some conformal factor. So sometimes these conformal transformations are also called conformal isometries of Minkowski space. Okay, so what we are interested in is that this omega x, you allow this transformation, you consider all the coordinate transformations such that your metric changes up to a conformal factor and not just exactly to itself. Okay, so and this condition, it turns out, is enough to completely fix all of the statements that I made here. So you can completely fix the transformations, and what you will find is that the set of, so obviously if since we know that Poincare transformations are a subset of this, Poincare will obviously be a subset of this, of the allowed cases. So let me write down the new guys, which is, so these are let me write down the most complicated one in some sense. So this is the special conformal transformations. Then x mu going to x prime mu, which is lambda times x mu, is dilatations. So this is special conformal transformations. This is dilatations. And then we have the ones that we are familiar with, which is x mu going to, this is translations. And then there is Lorentz, L mu nu if you like. So x mu nu. Okay, so this is your complete set of conformal transformations. So and just like, one second. So if you had omega x is equal to fixed, you could have derived these two things just from this demand, right? In exactly the same way, if omega x is left arbitrary, so then what it will do is it will tell you it will also fix. You will be allowed to have more general transformations, but the general form will be fixed. Yeah.
So capital omega constant is dilatation.
Yes.
And is it enough that the dilatation is enough to say that we have CHEP?
It's not enough to say that's at this level it is not. It's this is those two are separate in some sense. Okay, at this level they are different, but in general there exists most interesting theories or most local theories which are conformal, scale invariant or also conformally invariant. There are some counterexamples you can cook up and so on, but we will not care about them. So for instance, if most conformal field theories have a stress tensor. So if you are willing to sacrifice, for instance, a stress tensor, there is sense in which you can screw around with various things. I mean, even other counter examples exist. So but here, so at the moment I'm basically demanding that, I'm not demanding that omega x has to be a constant. Okay, so this is the most general transformation which does this, is this, and note that all of them come with some free parameters. This comes with 4 d free parameters, this comes with 1, this comes with d, and this comes with your d times d minus 1 by 2 or whatever. Okay, so also all together basically they should give you this many parameters. Okay, so you can write down infinitesimal versions, this, that, etc. of this, and you can work out the generators. There is a whole technology. So I don't know whether, so I'll just write down so typically one of the things that you're interested in computing, if you are given a symmetry and you want to compute the symmetries of, you want to compute a field theory. So what do you typically do? So for instance, let's say that you know that your theory is Poincare invariant. Okay, so there is a systematic mechanism, even though usually it's not done systematically in field theory courses, because when you have just Poincare invariance, we have a lot of familiarity with various fields and intuition and all that. So, but there is a standard technology with which one can construct the possible field representations of a given symmetry. Okay, at least in these cases one can construct it. So, in the case of Poincare invariance, so one of the statements about, one of the things that defines a field is that the translations basically act trivially. Okay, so that means that if you have x going to x plus a, so the field, whatever it might be, is going to be just phi x will go to phi of x plus a. Okay, so triviality basically means that there is no matrices or anything multiplying here. So if you have a matrix representation of a field, like for instance in the case of Lorentz transformations, you might have some spinor indices or tensor indices or whatever here. But that's not there for translations. So that's essentially, you can think of this as the definition of what a field is. Okay, so a classical field if you like. So, and the point is, so this sort of idea, so one can actually apply quite systematically. Okay, so I'm not going to get into it, but so most of the time what I'm going to tell you now is presented as a magical fact that why there are things called primary fields. Okay, but so I claim, even though I don't have the time to derive it for you, that this is actually not so magical. There is a well-defined way in which one can construct what the field representations of a theory are. Okay, so even in the case of Poincare invariance, you should have been a little bit more skeptical in your quantum field theory course to really ask why are the fields the way they transform, right? So, but if you believe that a general field, let's say phi a of x, a is basically the spin. So I'm writing it for Poincare invariant field theories, Poincare field theories. So what you will have is that you will basically have, this is how it will transform, right? So phi a of x. This is essentially what will happen. Phi b. Sorry. Okay, so this is what you will have, right? So let me make it actually quite clean. It's kind of important to keep everything clean. So let's say that you have a coordinate transformation like this, and this is understood that this is the Lorentz Poincare transformation, and if that is the case, your field phi a of x is going to go to phi a prime of x prime such that so this actually, what should I write? Yeah, so let me write it like this. So this is for conformal field theory. So SAB phi a of x. So this is how a classical field would transform. Okay, so in the conformal field theory case, if you are working with a classical field, the exact analogous thing would be, so now the understanding is that x mu going to x mu prime is a conformal transformation, and you will have,
shouldn't that be phi b?
Sorry?
Shouldn't that be phi b?
Oh yeah, yeah, that's right, sorry. So this is phi b, and so the claim is that you will have okay, so the point here is that this SAB is part of the definition of your field, and that's basically what determines what is called the spin of the field. Okay, so you're essentially when you're defining this, what you're doing is that you're saying that okay, your field is defined, the representation of the field is determined by its spin. Okay, so that's what you're really doing when in standard Lorentz invariant field theory. So here you need an extra bit of information, and that information is what is called the scaling dimension. Okay, and not just the spin. Okay, so here you just need the spin. Okay, so so this is the crucial difference, and a field that transforms like this is called, let me call it a primary field here. So this is called a primary field. So essentially it means that it's in some sense the irreducible representation of your, there is a sense in which you need to add more fields in order to fully talk about a full representation of the conformal group. So let me say that, no, I didn't want to say too many things, but somehow I'm getting led to that. So along with these, you also have the possibility of considering fields of this form, which are basically derivatives of these primary fields. Okay, so if you act with that, so these guys are also, so together, so there are two natural classes of fields in a conformal field theory. One is these primary fields, and these are basically what are called descendants. And together they form what is called a conformal multiplet. Okay, so the natural way, so if you think of this as the natural way of considering fields in Lorentz invariant or Poincare invariant field theories, this is the natural class of fields that one should consider in a conformally invariant field theory.
Is it necessary that the descendants actually derivatives of the conformal?
Is it necessary that it's, yeah, I mean, I think it is essentially coming from the conformal representation theory itself, right? So if you have these fields, so the full conformal transformation is not going to act just on one field, once, on one, this here, let's think about a scalar so that the discussion is a little simpler, so that this SAB is trivial. So this will be just phi and this is also phi. So if that is the case, you will basically also have to talk about derivatives of these guys so that the full conformal algebra is represented, it's a full conformal representation.
No, I'm asking, there can be other things than descendants also.
Like what do you mean?
Whatever will increase the factor is a descendant.
But it has to be, see, the fact that this is a derivative is important because that's essentially connected to the momentum generator in the algebra, right? It is not just that the scaling dimension changes. That's not the only crucial point here. Here it is also important that the algebra, which contains P mu, also, there is P mu, K mu, all of these guys are sitting there. So the generators, if you write, these are the, and delta. Okay, so these are the generators of this thing. And there is an algebra for this that you can write down, which is actually an enhancement of the algebra of just this and this. So Poincare algebra would have been this, just this. Okay, but then there is an algebra involving this as well. So this whole algebra has to be represented it has to be a field representation. So field representation, basically what it means is that the translations are represented trivial. That's what it means. So if you want to have that, then this is the natural way in which it should arrange itself. So I mean, if it seems a little bit magical, it's really not necessary for my discussion, which is why I was trying not to get into it. But the very basic idea, the rough idea is that even in the case of your even in the case of standard Poincare invariant field theory, what you really do is that because fields are realized in this trivial way, what you do is that you first identify how you define your representation theory very roughly. So you say that you look at the origin of field space. Okay, so let me say that there is some field like this. So there is some field which is phi of 0 with some spin. I will say that my field basically transforms like this. Okay, so I define my spin representation or the representation of the Lorentz group at the origin of spacetime. And then what I do is I can use my translations to move my field, right? I can do basically x mu, p mu, or maybe I should put it here better, times phi acting on 0, e to the minus I x mu p mu, or x rho p rho, let me put it. This will be my definition of my field at some new location. And now I can compute L mu nu on this because I know what the algebra of L mu nu is with P mu. So I can explicitly calculate how the phi fx transforms. Okay, and that is essentially how you get this version. This is kind of like an exponentiated version of that. If you do so I mean you can talk about an infinitesimal transformation, then it will be more transparent. But this is essentially how you fix these things. Okay, and in the case of the conformal field theory, what we are really demanding is that we start again with the same idea, which is that you start with the origin of spacetime, and then you look at whatever is the rest of the algebra that is left. Okay, here in the Poincare algebra case, if you fix your origin look at the field representations of the origin, what you have is the only things that are left are basically the Lorentz group, it's slightly easier to state these things in the language of Euclidean space. So it's basically rotation group. Okay, so and then you find the rotation representations, and rotation representations are basically labeled by these numbers called spin, as we know. Okay, That you can go look up if you're not familiar. That's a very basic fact. So, and once you have that, then you do, because you know how the translation generators act on the algebra and on the fields, you can construct it everywhere else. And that's how you define these things, even though it's usually not emphasized in that language. But in the case of conformal field theory, it seems even more magical, because this is sort of the systematic way to do it. And if you do it, you will get what I've said here. Okay, so the way you do that is, first you say that, okay, you look at the origin of space-time, and then you look at the field, you ignore everything except you keep everything except translations, because translations will move origin. Okay, so then you find, you write down the rest of the algebra. So I have not written down the algebra of, conformal transformations here, but you can look it up. It's essentially SO d, 2. Just the standard, SO algebra, but it's just that I have chosen my generators in some funny way, so it will rearrange in some interesting way, that's all. So, and once you have that, then you can write down the representations for dilatations, special conformal transformations, and spin, which is the Lorentz transformations, right? So that's how I write so I should basically have a set of fields. The generalizations of this guy in the case of Lorentz transformations should be something that is labeled by spin, the eigenvalue of dilatations, and the eigenvalue of special conformal transformations. But it so happens that the point is that so you can, I'm getting, way far afield. So the point is that just from the form of the algebra, then you can argue that K mu has to have 0 eigenvalue, and delta has to be a multiple of the identity. So that multiple of identity means that delta is essentially a scalar number, and that's that. And K mu doesn't show up anywhere because it is forced to be 0 by the conformal transformations. Okay, just from the form of the algebra, you can argue this. You see what I'm saying? So it is, so I don't know whether it was, at least I don't know, the moral was sort of clear, I hope. If you have any questions, I can, try to address that, but it's a little bit tangential to the thing, but I also think that it's important to make this a little bit less magical than what it is usually presented as. Okay? So a primary field is the natural thing that comes from doing the exact thing that one does in a standard Lorentz invariant field theory when the number of generators or the algebra is a bit bigger. That's it. Okay, this is exactly what you would get. So that's the definition of a primary field and its descendants. Okay, so So anyway, so for our purposes, even if you did not fully follow, you should have seen a little bit of conformal field theory to fully appreciate it, I think. But even if you haven't seen it before, this definition is enough for us. Okay, so and it's a natural generalization of what we had for Poincare transformations here. Okay, so now we'll, so the rest of the stuff, you can find in any conformal field theory book. It's not, I'll tell you some facts, and none of them are very surprising. The symmetries, just because of the symmetries of, conformal algebra is much bigger than Poincare algebra, right? So the fact that you want your fields to transform like this, and you want, just from that fact, you can fix the form of the 2-point function. And in Lorentzian signature, it basically takes the form for a scalar field. Okay, so so this is the form that it takes. So the Feynman propagator for a conformal field, for a primary scalar field. So scalar basically means the spin is 0, and phi has some scaling dimension which is delta. So just from using conformal invariance, you can fix this form. The important thing about this is that I have not computed it by solving wave equations or whatever, like one does in the case of standard scalar field theory. Okay, so that's not what I'm doing. I'm just using the fact that the theory has this much symmetry. That's all I'm using. So, and you can compare that to the case when the scalar field mass is 0, when the scalar field, a free scalar field with mass 0 is actually a conformal field theory with delta is equal to d minus 2 by 2. This is something that you are actually familiar with. If you actually do it in scalar field theory in 3 plus 1 dimensions, for instance, you will find that this is 4 minus 2 by 2, which is 1. So that's the scaling dimension of your scalar field, and this is basically the Feynman propagator for the scalar field, free massless scalar field, and delta is equal to 1. Okay? So, and this is, but the point here is that this is a generalization of that, and I have not used the actual wave equations or anything like that, which are all constraining me to free theory. Here I'm not making any statement about free theory, I'm just making a statement about the fact that the theory has conformal invariance. Okay? And that's why this is a very powerful idea, because you can, the correlation functions are getting constrained just using the fact that there are symmetry. So you might think that the theory, oh maybe there is nothing going on in this theory. That's not quite the case, because a higher point functions will actually be can be non-trivial. You know what I'm saying? So the fact that your 2-point function is known does not mean that the theory is free. So your 3-point functions and 4-point functions and so on can be non-trivial. Okay, so the whole set of correlation functions of the theory is still quite non-trivial, and it can be arbitrarily non-trivial. In fact, it is as non-trivial as quantum gravity in antidiscrete space. Okay, so that's essentially the statement. So I know that today's lecture, it's if you have not seen like field theory stuff too much, this is a little bit abstract. So feel free to ask questions. I don't have to necessarily cover what I have planned to cover today. Okay, we can slow it down a little bit and just ask questions. So if necessary. So the point. So if this is the part where probably like I kind of said a few more things than what is usually said, which I think is worth it, but at the same time may have been a little bit confusing. Okay, but the thing to take away is that this is the form of the conformal transformations on primary fields. This is the only thing that you need to know. Okay, so so now I'll just present a few facts. This is one fact. This again you can derive. Actually, I would ask, all of these. This is something that you can go and check. In fact, I think I strongly urge you, if you are interested in things of this nature, you go and work out, as this whole lecture as kind of an elaborate exercise. Okay, and if you have questions, you can come back to me and ask me. Okay, so so one condition which oftentimes we will use is that unitarity of the theory forces delta to be scaling dimensions of all fields have to basically be greater than d minus 2 by 2. Okay, so in the limit when this bound is marginal, then the theory is free. Okay, so that's one fact. Yeah, and the second fact that we care about, so we will generally, of course, as I said, 3-point and higher point functions of these correlators of these fields are very interesting, and they contain a lot of information. Okay, so we will, so they contain a lot of information. So, and we will talk, but ultimately we are interested in the ADS side of the story. Okay, so we won't need much of it. So one fact that I will need in order to connect with ADS CFT is that if you remember last week, I drew a picture of ADS which was like this. And if the boundary of ADS is the cylinder, I would naturally need to look at CFT on cylinders. Okay? So, and the idea here is that, so the metric on this cylinder, so this is sometimes called the Einstein static universe, which is, I'm setting the radius of the cylinder to 1. So this is the metric on the cylinder, and this, so this is just the boundary. Okay? So typically, if you remember from our discussion about path integrals and all that, there are two different ways in which we describe our fields. So one is in terms of field, in terms of the basis of the field, of the Hilbert space. One is in terms of field configurations, and the other is in terms of, let's say, eigenstates of a Hamiltonian. Okay? So this language applies also in the case of CFTs on cylinders. So the point is that, so the Hamiltonian in the cylinder language is basically an operator that shifts the time in the, t going to t plus a. That's what the Hamiltonian is. Okay? So let's go to, there is in Euclidean signature, the metric of the plane. So let me see how this can be connected with what we know about the Euclidean So our theory was basically in Minkowski space or its analytic continuation, which is Euclidean space. Okay. So but this is not that. This is basically, this has curvature and this is just a line. So this is R times some SD minus 1. Okay. So and this has curvature. This is not a flat space. Okay. Yeah.
So in this CFT, this length, the form of the Newton function is the same.
It will transform, right? Because we know how the field will transform, we just have to transform it according to this and you will get the formula. But so there is one more subtlety, unfortunately, which is related to the fact that, so when I defined conformal field theory here, what I said was that my field theory, it is a field theory where the, you know, the metric basically transforms to the, you know, the Minkowski metric basically transforms to an overall factor times the Minkowski metric, right? But this is not Minkowski metric, even if you multiply it by an overall factor. So, but it turns out I'll write down an equation which is a slight generalization of what I said about Minkowski space. See, there are, yeah, I mean, as I said, you know, this is one lecture which is unfortunately has to be a bit compact, but it contains various little points like that. So, yeah, I mean, it requires, you know, like I taught a whole course on ADS 51, so it's not like we cannot, so you'll have to kind of take a few facts at face value, unfortunately. But yeah, so you're correct in the sense that what I said so far is not quite enough to make a connection with the cylinder. Because what I have said so far basically connects Minkowski space to Minkowski space times some Weil factor. But this is not Minkowski space times any, I mean, if you multiply it by a Weil factor, it will become Minkowski space. But this itself is not Minkowski space. So the statement that I made earlier was about transformations of this kind, where this was Minkowski space and this was Minkowski space, but such that when x went to x prime, this became some non-trivial thing. So this was a statement. Okay, but that's not this situation. This situation is a little bit different, but I'll explain what exactly. I'll make the statement about why exactly this is still accessible within conformal field theory. So that's what I'm actually going to do now. Okay, what I'm going to do is I'm starting with, and there is, unfortunately, there is one more lie involved, which is that this is in Lorentzian signature, and Lorentzian signature cylinder is what we are really interested in. But Lorentzian signature, there is one more issue or thing that one has to worry about. So what I will do now is I will show or argue that Euclidean correlation functions on the Euclidean cylinder has a natural map to CFT correlation functions on the Euclidean plane. And then I will let you believe that similar things can be argued for Lorentzian signature, even though it's not completely true. Because, yeah, you can ask me later. Okay, so the Lorentzian signature thing is a little bit more tricky, but not unduly so, because there is one more analytic continuation involved. So you first have to go from Lorentzian plane to Lorentzian, Minkowski space, Euclidean plane to Lorentzian plane, then go to Euclidean cylinder, and then do one more Wick rotation. So there is a question of commutation of these things, and it doesn't quite commute, but we can still argue that the correlation functions that you're interested in can be extracted in a useful way. Okay, so what I'm going to show now is to show that in Euclidean signature, we can write our flat space metric in this form. This much is clear. And then what we do is we define our rho is, there is a new coordinate that we define, and under that you get d tau square plus d omega square d minus 1. Okay. So, and the point here is that, the point here is that this is this up to the Wick rotation. Okay, so you started with Euclidean plane, did a coordinate change, and then we find that the resulting metric is conformal to the cylinder. So the reason why, the statement, the reason why this is a useful or interesting thing to do is because of this observation that one can justify. So if you have a correlation function of this form, okay, so I'm evaluating this correlation function on a space-time where it is conformal to, let's say, Euclidean plane. Okay, and that such a correlation function one can show where the delta 1, delta n, etc. are the scaling dimensions of all these guys. times the correlation function evaluated on delta mu nu. This is actually a quite simple statement to show, but it's a distraction for us, unfortunately, again. Okay, so, and this statement, so there are a couple of again subtleties here, which is that it is something there is in conformal field theories. So this is here I'm assuming that my correlation functions are normalized. Okay, if it is not normalized, I have to worry about something called a conformal anomaly factor here. And that conformal anomaly factor will, it will again, I don't want to mislead you because this is an important thing in some cases, but it will not play a role for us. Okay, so if it is these kinds of, when you do a while transformation on metrics, the correlation functions transform in this way if the theory that you're working with is conformal field theory. This is a bit more than what I started off by saying about conformal field theory, which is a statement only about, you know, Euclidean plane conformal field theory or Lorentzian conformal field theory. It was only about that, but now I'm saying a little bit more here. But it is easy to kind of argue, especially if you start some path integral definition of a field theory, you can basically argue that this just automatically falls out. If you have, if your metric is changing by a while factor, how does your correlation functions change? Okay, and in fact, it's from the lack of invariance of the measure in the path integral that you basically get this anomaly piece that I was talking about. Okay, and that anomaly piece does not depend on the correlation function, it's a property of the theory. And in fact, it doesn't even depend very strongly on the properties of the theory. It just depends on what is called one number typically, which is called the central charge. Okay, so if so in many ways it's a very simple dependence. So and and in most cases, so here we have gotten rid of it by normalizing the correlation function. Okay, so the point here is that, so the reason why that was important for us is because we will ultimately be interested in the cylinder. Because cylinder is our boundary for our radius, and we are interested in computing correlation functions of CFTs on cylinders. And the claim is that if we know how to compute correlation functions of CFTs on planes or on Euclidean spaces, then you can compute it on the Euclidean cylinder by doing something like this, and then we can analytically continue and so on. Okay? So this is the sort of the statement. Yeah, there will be extra stuff. Here I'm just writing it for scalar fields. Yeah. So you can, so I mean, so also for descendant fields, etc., things will be more complicated, slightly more complicated. But once we know these things, the rest are, we can compute if you want. So that's the claim. So yeah.
So we are saying that the effect y transformation has only these two relations.
Mm-hmm.
We are saying that the effect conformal transformation should have.
So but it's in some sense a question of interpretation, right? I mean, we are in one case we are only talking about conformal transformation. When you say about conformal transformations on the Euclidean, or sorry, in the Lorentzian on Minkowski space, then what we really are saying, we are trying to extract statements about correlation functions and so on. Okay, here what we are trying to do is that we are saying that, okay, we are going to do a while transformation on our space-time, and when you do a random while transformation, the space-time will change. Okay, so basically, so this is, you have redefined your this is a coordinate transformation, and the result of that, this here it was, let's say Minkowski space, but this guy is not Minkowski space anymore. And what we are saying is that if you wanted to compute the same theory living in this new space, what one should do is do this operation. This is what we are saying. So here, so in the previous case, it was just an invariance of a given theory. Here on the other hand, what we are doing is we are using this conformal transformation to compute these correlation functions in the new space. So that's the difference. So here, like it was, I mean, it's basically an invariance. So the theory has, this particular invariance. So the correlation functions, we can fix the correlation functions because we know that it is an invariance. Here on the other hand, we assume that we know the correlation functions and then use that to define your correlation functions in the new space. So that's the difference in philosophy. Okay? Any other questions? Okay. So, right, yeah, so these are, I'm basically, this part at least I'm, kind of following again Harlow, so you can go take a look at this. And if you have any questions, you can come back to me. Now I feel like it was a little bit more terse than, but on the other hand, this is the only story we need. So if I just slow down, you will feel more comfortable. So slow me down, that's all you have to do. It's not like, if you have not seen conformal field theory, I know that it is a bit quick, but we just need a few facts, and that's where we are headed. Okay? Okay, so yeah, so I think that's all the conformal field theory that I need for the moment at least. So if we need something else, we will come back again. So with this, with our discussion from last time about the ADS side of the thing, and from discussion of today about CFT, we can make a statement about ADS CFT correspondence. Okay, and the statement is essentially a definition. The definition of ADS CFT correspondence is that conformal field theories are basically quantum gravities in asymptotically antidescript spaces in one higher dimension times possibly some compact space. So that's the definition of the most general expectation about conformal field theories or ADS CFT correspondence. Okay, so that's the statement. So that's if it is just a definition, then the question is, well, how are we going to extract some meaningful, useful things out of it, right? So, and what we want to do is, the first thing we want to say is that a general conformal field theory clearly doesn't look anything like general activity, right, in ADS. So when does it look like general activity in ADS? That's sort of the first and basic questions that one might ask. And also I should say that, in fact, it is because the CFT, in a way, the weakness of ADS CFT is in fact I would say its strength. Which is that if it was kind of like the case that we understood string theory or the full non-perturbative string theory on the gravity side, kind of independently, then it is not so useful in understanding that. You know what I'm saying? CFT here on the other hand, because we have a definition of CFT which you can check in some limit, in the large n limit, like as I was saying in the last lecture. So at finite n, you can use CFT technology to in principle understand bulk quantum gravity or string theory or how to define it, etc., etc. Okay? So the main question that we are first going to tackle today is, what classes of CFTs have holographic or have semi-classical holographic duals? Holographic duals. So this is the first question, and this will be a question that is of interest to us. And I already talked about large n factorization and free theories and all that long ago in one lecture. If you don't remember it, I'll probably sort of repeat it here. So this means semi-classical holographic dual basically means that this is the same statements as weakly curved. Weakly curved means the ADS length scale is large compared to both the string scale and the G Newton, Planck scale. Okay, so there are two length scales that we talked about. One is this alpha prime, which is I think LS square. Okay, and then there is this is one length scale, and then we had Planck length. So the claim is that we want our theory, so the length scale capital L of ADS that we started with would be in the semi-classical limit, where general activity becomes more and more standard general activity. That happens when L and suitably defined L, and L is much larger than alpha prime, square root of alpha prime, and LP. So this is what we mean by this semi-classical holographic dual. So I wrote down in yesterday's class a few formulas. So I wrote down that LP to the 4 is GS alpha prime square. Okay, so this is the 10-dimensional Planck length. Okay, so and I also wrote down that so there are two formulas that I wrote down, right? I wrote down 4 pi times GS is G square Yang-Mills on one formula. The two main Maldacena formulas are this one and the statement that I wrote it like, so using this formula, this LP to the 4 is this, I can write the other formula that I wrote down as in this way. Okay? So alpha prime is LS squared, a string length squared. So, and using that, I think this lecture, yeah, once you're a little bit familiar with this lecture and the last one, yeah, I think that the rest of the going should be fairly straightforward. So again, using the fact that LP contains GS and alpha prime square, and alpha prime square basically becomes LS to the 4. Alpha prime is LS square. This is the definition. So using that, we can also write this as R by LS to the 4 is G square Yang-Mills times N. Okay, so I'm probably not keeping track of some 4 pi here, so let me just write it like this. So the key formulas for us are these. So this is another way to write the Maldacena formula, which is in many ways quite instructive. So the claim is that, I think, did I call it R or capital L yesterday for ADS length scale? So let me just change that then. So this is L, this is capital L, and this is capital L. Okay? So any questions? So this was the observation that we made last time, was that the G string on the bulk side goes as G square Yang-Mills on the gauge theory side. So this is the right hand sides are gauge theory quantities and the left hand sides are string theory quantities or gravity quantities. Okay, so this is G string, the coupling of the string. So the string has G string, which is a coupling, which is a dimensionless number, and then there is a dimension full parameter, which is alpha prime, or you can equivalently think of LS. So these are the two things that define a string theory. And when you are working with ADS spaces, there is one more dimension full quantity, which is capital L. Okay, so on the string side, we have GS, alpha prime is equal to LS square, and capital L. So at least in the semi-classical, weakly curved ADS limit, there is 3 parameters that you have available on the ADS side. But on the gauge theory side also we have parameters, which is one is G square Yang-Mills and N. Okay, so and these are the Maldacena formulas which relate the two. This is basically coming from string theory. How you define, from string calculations, how do you get the gauge theory amplitudes and so on. So we had a brief discussion about it last time, and so that's where this comes from. Okay, so the point is this. So this object here is sometimes called the Toft coupling. Okay, so there is again many words are coming at you, but yeah, so to understand the story, I think you just have to kind of not get too confused. Okay, so that's really all you need. So the story is basically that. So you can think of the gauge theory quantities either as G square Yang-Mills and N, or you can think of it as lambda and N. And this is the natural language in which it connects with string theory. Okay, so instead of G square Yang-Mills is not the most natural variable to connect with string theory. Instead it is this particular combination of G square Yang-Mills and N, which is called the Toft coupling. Okay, so this lambda and N are basically, so what it is really saying is that L by L string to the 4 is basically lambda, and L by L Planck to the 4 is basically N. So some powers will change if you go from ADS 5 times S5 to somewhere else, but all of, some positive power. That's all you have to remember. Is that okay? So what it is really saying is that it is a double expansion. So gauge theory is in the large N limit of a gauge theory, when N is very large, what you're basically doing an expansion in 1 over N and lambda. So this is what is called the large N expansion of a gauge theory. Okay, so this was first done by Toft, and that's the reason why this lambda is called Toft coupling. So what Toft realized is that instead of working with this G square Yang-Mills and N, it is convenient and things simplify in the large N limit when you work with this lambda and N. Okay, so this is sort of the double expansion one works with, and this is sort of the same language in which string theory also one should think about. So in string theory also we have this natural notion of an expansion in loops in string theory, which corresponds to this expansion, and then there is an expansion which is sometimes called world sheet perturbation theory, which is in lambda. So the picture is basically that if you have seen pictures of closed string expansion, you would have seen pictures of this kind. Okay, and the claim is that each order of this, basically roughly speaking, you can think of it as 1 over n, further and further, and on each of these things you have a conformal field theory which you are doing an expansion which you think of as in lambda. Okay, so yeah, so this is again a little bit tangential and you don't really need it, but the only part I kind of wanted to really emphasize is this box here. Okay, so there is a double expansion, and the expansion is in 2 parameters. One of them measures how big ADS is in string units, and another one measures how big ADS is in Planck units. Okay, and these corrections, these corrections are sometimes called, these corrections are truly what are sometimes called quantum corrections. Okay, because these are associated with L Planck. Okay, so these are again some couple of words that we need. And any question on the terminology? I haven't really said much more than what I've said last time already. Okay, but on the other hand, it's good to kind of say that one more time so that it sinks in a little bit. Any questions? Okay, so maybe I think since this may have been a little bit too quick, not too quick actually, but it's maybe the first time you're seeing it, maybe too much material for one day. So I had a little bit more to say, but I strongly encourage you to go look at this and the previous lecture, otherwise you're increasingly going to get lost in the next lecture. Okay, so we need kind of this, you really don't need, so as I said last time when we started, last time I think the class, I think you followed better. I think today was in the conformal field theory was a little formal, but so the thing to keep in mind is so you don't really need to know all the background, but there are some key points that I'm emphasizing you should kind of know as facts. That's good enough. Okay, and we cannot cover everything, but by all means, if you have questions on the things from yesterday's lecture and today's lecture, especially today's lecture, you can come to me. Okay, you can send me an email or come to me. I think that's probably better, because last time's lecture, I think that the story of string theory, I think I said it was somehow a very linear story, so it was easy to tell. Okay, but here on the other hand, there are various pieces that I have to pick from various parts of CFT, so it may not have been that clear. So if you have questions, you by all means come back, and today's lecture we will need, and I don't see a quick way of covering the essential parts of conformal field theory without having some amount of shock in it. Okay, so you can just ask me. So anyway, to make your life a little bit easier, I'll stop here for today and take questions if there are any. Okay. Yes, go ahead. So these deltas are basically what, so when I define this primary field, right? So what I was saying was that just like your, like if you have a standard quantum field theory, your field will transform like this. Standard quantum field theory in Poincare invariant quantum field theory. But, so these are the natural fields with which we work. Okay? Note that, so which operators we choose to work with is in some sense what we are trying to decide. You know what I'm saying? When we are trying to work with a quantum field theory, there are some arbitrary things you could take. You could take some operator, take one component of Lorentz invariant thing and do all kinds of arbitrary things. Add it with some other component of some other thing. That's a perfectly well-defined operator in the Hilbert space. So the point when we are trying to work with a specific class of operators, these are the basic operators or local operators of theory which are interesting and which in some sense form the fundamental set. So that's what we are really trying to do when this is at the level of just Poincare invariant field theory. That's why we are interested in them. So the question is whether there exists such a natural class of operators in the context of conformal field theory on which the conformal transformations act nicely. Okay, so they form representations of the conformal field theory. So that's what we are trying to do. So because that is necessary in order for the theory to have conformal invariance in its correlation functions in the way that we were discussing. So if you have a conformal field theory, the claim is that, so these numbers, these SABs that I introduced here, these are determined by, so if you, let's say, if I'm doing x prime mu, which is lambda mu nu x, let me just write it properly. So I think this might be a bit, I think that's a good question. So let me just say that. So this is what a Poincare transformation does. Okay, so and a field is basically, what it does is it basically goes to SAB, and it's a function of this lambda, and it takes it to phi b. Okay, so this is what it really does. Okay, so the point is that these are just parameters, and the specific choice of this matrix AB is what is controlled by the spin of the field. So once you specify the spin of the field, and the spin of the field is basically some half integer number. Okay, so if you give me a spin of the field, I can always, given that spin, I can compute this SAB lambda. It's fixed, it's known. If you tell me that it's a spin half field, or half zero or whatever according to spinor and so on, once you give me that, this matrices are known. So in exactly the same way, in a conformal field theory, what happens is that I need to give you not just the lambda, I also need to give you so instead of not just the spin, but I also need to give you one more number, which is basically what I was calling delta. So that's a property of the fact that it is a generalization of Poincare invariant field theories. That's why I need one more number. Okay, so if you think of the spin as part of your definition of the field, here you also need a new number which I will call delta, in order to define the natural fields of the theory. And what I was saying was that instead of this guy here, I will have dx prime by dx to the power minus delta times this SAB, which is again a function of lambda. I did not emphasize that, but it is always true. Okay, so phi b. So this is the structure of the transformation in a conformal field theory. Okay.
Each field they could be.
Sorry?
For each field they could be.
Yeah, so the point is that, so what you mean by field is something that transforms in this way. So for instance, when you say Dirac spinor, there is a particular choice of SAB that you write down. Okay, so that's the choice of my field. So I am saying that my choice of the field here is dictated by SAB choice and this delta choice. So if you give me that, that's what I understand by a field in conformal field theory, and it has a specific name, primary field. So a primary field is just, it's the analog of a Lorentz invariant field. You could call it a conformally covariant field if you like. It's a Lorentz covariant field. That's a conformally covariant field. Okay, so the point is that we are interested in them because those are sort of the basic ingredients from which we can hope to construct conformally covariant correlation functions. So if it is just randomly, if we take one component of a Dirac spinor, it has no interesting transformation properties. Its meaning is not clear to us. Okay, but if you write down, so because we know that our theories are Lorentz invariant or Poincare invariant here, we know that its correlation functions have to satisfy, transform, covariantly under Poincare transformations, and these are the fields that will help us do that. So these are the natural local operators in the theory which help you write down these correlation functions, and analogously here, the same sort of thing here. And the only difference is that, here I was able, because I did not, again, this is another fact, if I say it as a fact, it's a very simple and basic fact, but at the same time, it is not true in standard Poincare theories, is that you cannot fix the correlation functions, two-point correlation function completely if you only know that the theory has Poincare invariance. Okay, you can fix, the spin structure you can fix, and you can also say that the two-point function should be translation invariant in spacetime. So those are the only two real statements you can make. But here, because the symmetry is so much bigger, it has d+1 more generators, because of that it turns out that you can actually completely fix the two-point function once you know my delta and my SAB. That's it. Okay, so this fact is, I just wrote down the correlation function. You can systematically do it, and it's not very hard even. But the point is that the fact is what is important for us. Okay, so the fact is important because it is not true in Poincare invariant field theories, but it is true in conformally invariant field theories. Yeah.
So the form of that two-point function that you have written, it is only for primary field.
It's in the case of scalar fields, it doesn't matter. You know what I'm saying? So the two-point function will actually, the two-point function I wrote down is only for a scalar field. Okay, so the structure of the two-point function will change when there is spin. So, I mean, but it's not, those are just spins, those are completely fixable, and we don't care about them. So we can, there are papers by, I can give you references, Osborne, and, the people have written these things down very explicitly. But we don't really care about those things, because the crucial feature that is fixed is basically the 1 by x minus that structure. So the rest is mostly tensor structures corresponding to spin. So it doesn't really matter for us. So, but yeah, so for once you know the scaling dimension, essentially the field is, the correlation functions are fixed.
What about the generalized free fields?
So generalized free fields are, okay, so generalized free fields are, so the 2-point function, generalized free fields are ultimately just some particular class of operators or the particular class of primary fields. So they are basically a particular class of primary fields which are called single trace operators. So the 2-point functions of single trace operators are fixed. I only talked about 2-point functions yet. Right? So if you compute n-point functions are anyway not fixed completely by knowing this delta or this j. They're not fixed. You also need extra information which is related to the details of the conformal field theory. And that details of the conformal field theory in the class of, in the holographic theories that we are, holographic conformal field theories that we are interested in, those details are controlled by 1 by n. So you will see that we will talk about. I was planning to cover it today, but that we will get to in the next lecture. So yeah, but these are good questions. So I think that these are the kind of questions that will kind of anchor the lecture to, what is, so if you have anything else, I have another 5 minutes. Nothing else? Okay, so I think that's, let's stop here for today. But by all means, please look at, it will be online by maybe in a day. So please look at what we talked about today morning, and if you have questions, do come back, because I think it is kind of important.